So I think we're ready. So Hanlin came all the way from Oxford and he'll tell us about really beautiful stuff.
Thank you, Eric. It's my great pleasure to also a great honor to present here on something called iterative win-win method. And this is based on joint work with Li Jie, Shuiqi, Zhenjian, Igor, Rahul, and I also cover a later improvement by Zeyong Li. I guess the title is somewhat like confusing. So what does the title mean? Oh my God, my computer is a bit slow. Pardon me. So first, the main subject of this talk is something called the iterative win-win method, which is some interesting technique that complexity theorists might care about. Some spoiler, it's like this method is used to perform some win-win analysis, and traditionally we have some kind of win-win analysis that gives us non-trivial results, but this kind of method has the potential of getting near optimal results. And so far, this method has been effective on so-called explicit construction problems, which are actually, I mean, explicit construction for random or pseudo-random objects, like Ramsey graphs and circular bounds, and something called range avoidance, if you know what that is. And finally, there is I added without using it in the title, and hopefully you'll see what it means in like when I proceed later. So let's begin by the problems that we'll consider. Sometimes we also call this problem finding a hay from haystack. So this means we want to solve search problems with a lot of solutions. So many solutions such that even if you pick a random string, it's a good solution with like good probability. So how hard could it be to find a hay from haystack? But it turns out that this problem was like some problems like this are really hard for maybe complexity theorists to do. For example, like a famous example is to construct Ramsey graphs, which are n-vertex graphs without cliques or independent sets of sides like 4 log n. Paul Erdős famously used the so-called probabilistic method to show such graphs exist. Actually, if you randomly select an undirected graph, like each edge is included with probability exactly half and independently, then with high probability, such a graph will be a Ramsey graph. But we don't know any deterministic construction yet. So we don't have so-called explicit constructions for Ramsey graphs with such parameters, despite that such graphs are abundant. If you randomly pick one, then it's a good Ramsey graph with high probability. I think in this year's Fox, Xin has a improved construction of Ramsey graphs where the clique and the independent set is polylog. I think this is considered as a breakthrough. By the way, Paul Erdős has a $100 prize on explicitly constructing a Ramsey graph. So, and another example is to Oh, I see. Yeah. Yes. Another example is to construct prime numbers. So given an integer n, we want to produce a prime of like magnitude exponential in n, which means n-digit prime or n-bit prime. By the prime number theorem, a random integer of magnitude like 2 to the n is a prime with probability roughly 1 over n. So if you randomly sample such an integer, you have a decent probability of hitting a prime. This problem is hard because ChatGPT doesn't solve it, and it's also It's also a very hard problem for number theorists. Like previously, there is a polymath 4 project which wanted to use number theoretic techniques to get a faster deterministic algorithm for finding primes, but unfortunately, they didn't get unconditional improvements. In general, there's this big question in randomization. If I have a search problem which can be solved very easily using randomness, can we also solve it without randomness? This question is widely open, even for many interesting special cases like Ramsey graphs and finding primes. Here is a third example of explicit construction problem, proving circular bounds. Why is it an explicit construction problem? Because Claude Shannon around 70 years ago proved that most functions require exponential circular size. He also did it by a counting argument. So if you randomly sample a function with high probability, you will get a exponentially hard function. But the proof doesn't give you any construction of hard functions. Maybe later generation can find one. Later generation will find it very hard to find hard Boolean functions. Actually, we are like making very limited progress on proving circular bounds. The current best lower bounds are like depending on how you define circuits. The current best lower bounds are 5n or 3.1n. But the existential bound is like exponential in n. So what's going on? We don't even know if there are functions in E to NP that requires superlinear circular size. E to NP is a gigantic class containing that is computable in exponential time with an NP oracle. So I think we even believe like SAT require maybe like exponential size circuits, but we are far from proving even a like superlinear lower bound for E to NP. Recently, or maybe not so recently, there has been a work on complexity theoretic explicit constructions. So the aim is to use complexity theoretic ideas to solve these explicit constructions, or at least get better bounds. This is a natural and fruitful approach to study explicit construction problems, and we are already making some progress here. For example, in Stock 27, Igor and Rahul presented a so-called subexponential-time infinitely often pseudo-deterministic construction for primes. So this is some improvement over the naive algorithm for primes, which needs exponential time, but it also has a few caveats like infinitely often and pseudo-deterministic. So let me kind of explain what is a pseudo-deterministic algorithm, because later we also have an improvement of this result. We say a randomized algorithm is pseudo-deterministic if on most branches, on most random computational branches, it will output the same answer. So, so a deterministic algorithm only has one branch, and let's say it finds a prime, then this branch contains a prime. For a randomized algorithm, it has it throws polynomially many coins, then it has exponentially many branches. For let's say 2/3 fraction of computational branches, it will find a prime. And on some other computational branches, it will output failure. For a pseudo-deterministic algorithm, we not only require like most branches find a prime, we require that most branches find the same prime. So maybe some branch will fail and some branch will output a different prime. These branches are bad, and we require the fraction of bad branches is, let's say, at most 1/3. You can amplify the success probability to like exponential in n, or 1 minus exponential in minus n, something like that. Mm. Yes. Yeah, so if it's a decision problem, then randomized algorithms and pseudo-deterministic algorithms are the same thing. But if it's a search problem, then pseudo-deterministic algorithms have the additional property that it with high probability always output the same answer. Another way to look at it is like if I have a bounded observer, then it will think the algorithm is deterministic because it just runs the algorithm for a few times, and each time it gives the same answer. Yeah, I think Iran Gat and Shafiq Al-Wasser so the result of Igor and Rahul was about this notion of pseudo-deterministic algorithms. They showed a pseudo-deterministic algorithm A that given the length n of prime you want to construct, runs in sub-exponential time and constructs an n-bit prime, but their algorithm only works for infinitely many n. We'll see soon like how this algorithm operates. Can you see it clearly? Like for the green text, any dense language. So they proved the theorem not only for primes, but also for any dense language decidable in polynomial time. So prime is dense by the prime number theorem and is decidable in polynomial time by the AKS primality test. Therefore, the result automatically holds for primes. But primes is a prime example of dense language in polynomial time whose explicit construction problem seems hard. I think this result illustrates some features of complexity theoretic constructions, like it works for a large class of construction problems like any dense language in polynomial time. It can sometimes make progress on some problems that are otherwise hard to tackle, even like for primes, even even if we know so much about like number theoretic properties of primes, it still seems hard to get deterministic algorithms for constructing them. But using complexity theoretic ideas, we get pseudo-deterministic algorithms. And one downside is that it's like in many cases, it doesn't give you deterministic polynomial time construction, and it have a few caveats like pseudo-deterministic sub-exponential time infinitely often. Their proof idea is perhaps even more interesting than the result itself. They use some kind of win-win analysis. So so condition on some complexity theoretic statement. If the statement holds, then the algorithm is something. If the statement doesn't hold, then the algorithm is something else. Precisely, the statement is whether P space is equal to BPP. If P space is equal to BPP, then randomness is powerful because you can construct a prime in P space, which means you can also construct the smallest prime in P space, which means you can also construct the smallest prime in BPP. So you get pseudo-deterministic polynomial time. If P space is not equal to BPP, then we have some Hardness-randomness. We can use some Hardness-randomness trade-off to get deterministic construction. Let me also mention the parameters here, where if P space is equal to BPP, then you get polytime construction. Otherwise, since you only get super poly hardness, you only get like sub-exponential time construction. I think we can. Actually, our new result is stated as a single algorithm, but their result is stated as like only an existential result. I think they can combine it. So why did they stop at sub-exponential time algorithm? Because what they are actually doing is a win-win analysis over two input lengths, N1 and N2. So let's say N2 is somewhat larger than N1, and we have some condition on N1 and N2, which is some finite version of P space equal to BPP. If the condition holds, then we can construct an N1 bit prime in poly N2 time. If the condition doesn't hold, then you can think of we have a PRG over length N1 that fools N2, which means we can construct an N2 bit prime in poly of 2 to N1 time. So I think I omitted some polynomial factor here. Maybe this is N1 to 0.1 size prime, but that's not important here. So let's plot a graph and see what is the optimal relationship between N1 and N2 that will enable this construction. In the, we fix N1 and let's see what's the best N2. In the yes case, if the smaller N2 is, the faster the algorithm is. And in the no case, the larger N1 is, the better your hardness condition is. So the faster the algorithm is. Since we use the win-win analysis, we don't know which case will happen. We will always take the worst one of our algorithm. So the overall algorithm is like this blue line. Turns out that if you set N2 to be something called half exponential in N1, then the overall algorithm will run in half exponential time. A function f is half exponential if after you compose itself with itself, it becomes exponential. So I think there are no elementary description of such half exponential functions. And I guess this is also why Igor and Rahul stated their algorithms as sub-exponential time, not half exponential time, because that's easier to digest. Yeah, somewhere in the between. So you can see that if you just use this win-win analysis, you cannot get quasi-polynomial time algorithm or even polynomial time algorithm. I will revisit this example later, but now let's see another example of explicit construction problems. I don't know, if you can. I don't know if you find it easy to treat circular bounds as explicit construction problems. So this is a very old example where 40 years ago, Ravi Canton proved that actually what he proved was sigma 2p requires a fixed polynomial set circular bound for sigma 2p. But if you want to scale it to circular bound for exponential time, then it's something like sigma 2 exp is not in polynomial set circuits. So in the second talk, I will elaborate on how to view this lower bound as explicit construction problems. But for now, let's just think this is an explicit construction problem. Canton's proof. Yeah, I think I have 1 or 2 slides on it. Yeah, I think I have 1 or 2 slides on it. Thanks. So interestingly, this lower bound is also proved by win-win analysis. Besides that, Canton also needs the important theorem by Karp-Lipton. The theorem says that if exponential time, okay, maybe this is also not the original version of Karp-Lipton, but it's definitely mentioned in the paper. So it says if exponential time requires, it's in polynomial sites, then exponential time collapses to sigma 2p. So notice how sigma 2p appears in the Karp-Lipton theorem very naturally. And this is related to the circular bound. You mean non-uniform upper bound? You mean non-uniform upper bound imply uniform upper bound? So given this theorem, we can also use a win-win analysis. We condition on whether exp is equal to sigma 2p. If they are indeed equal, then sigma 2p is powerful, so we can use diagonalization in sigma 2 exp. In particular, we know that you can create a hard function in double exponential time. If exponential time collapses to sigma 2p, then this is sigma 2 exp. On the other hand, if exp is not equal to sigma 2p, then by the Kaplan theorem, we directly have a circular bound for exp, which is also a circular bound for sigma 2 exp. So in either case, the circular bound will hold. I also want to notice that this win-win only gives you superpoly lower bounds. In the first case, you can get exponential bounds, but in the second case, you only get superpoly bounds. Of course, you can still like adjust the parameter and get better bounds. But let's see, like what's the best bound you can prove for sigma 2 exp? You can kind of scale up, scale up or scale down the Kaplan. I think it's scale up the Kaplan theorem to show something like if exp has Fn side circuits, then exp is in sigma 2 time polynomial in Fn. So I'm again omitting polynomial factors here. So if we want to prove a circular bound of size Fn, this is the Kaplan theorem we will need. We branch on whether exp is in sigma 2 time Fn or not. If it is, then sigma 2p is powerful. So you can do diagonalization in sigma 2 time. I'll calculate the parameters later, but let's put question marks here. And if exp is not in sigma 2 time Fn, then we get the desired circular bound against size Fn. So what remains is to calculate the question mark here. We know that we just want circular bounds of size Fn, so we need like 2 to O Fn. I think it's 2 to Fn log Fn time to diagonalize and create a true table with Fn hardness. If we only have exp is in sigma 2 time Fn, then in order to simulate a 2 to Fn time algorithm, we will need a f of Fn times sigma 2 algorithm. Therefore, if we want our hard language to be in sigma 2 exp, we will need f of n. It's almost 2 to n, which means f is sub-half exponential. That is, Cannon's win-win argument can only give you a half exponential circular bound for sigma 2 exp. Now, let me introduce our two results. Roughly speaking, we improve the pseudo-deterministic construction and Cannon's lower bounds into like an optimal win-win analysis. The first result is to improve the pseudo-deterministic construction of primes, or in general dense properties, into an optimal polynomial time algorithm. And somehow we overcome the half exponential barrier by a new win-win analysis. And our second result is to improve Cannon's lower bound and prove a near maximum lower bound for sigma 2 exp. So we show that sigma 2 exp does not have 2 to n over n side circuits. You can replace 2 to n over n by any bound that any lower bound that can be proved by the so-called probabilistic method. So I believe the current bound is slightly above 2 to n over n, but anyway, this improves the half exponential bound of Canton to a truly exponential bound. And our second result also implies something, implies an algorithm for some problem. So the algorithm is a so-called infinitely open single-valued F sigma 2p algorithm, which I'll define in the second half of the talk. And the algorithm is for a problem called range avoidance, which I'll also define in the second half. Here, and I'll have, like in the rest of the first talk, I think I'll talk about the iterative win-win technique and like how to use this to prove to get a pseudo-deterministic polytime construction for dense properties in P. Roughly speaking, previous win-win arguments are like, we have some condition on impedance N1 and N2. If it holds, then we solve impedance N1 in poly N2 time. If it doesn't hold, then we solve impedance N2 in exponential in N1 time. And this win-win analysis will start at a half exponential barrier as we calculated before. In our new win-win analysis, we do something like the following. We select impedance N1, N2, N3, and so on. So we have, if something good happens, then we can solve impedance N1 in poly N2 time. If this good thing doesn't happen, then we continue our win-win analysis and look at another good thing. If the second good thing happens, then we solve impedance N2 in poly N3 time. If it doesn't happen, then we look at the third good thing. If it happens, then we solve impedance N3 in poly N4 time, and so on, until we reach impedance N of little t. If every good thing didn't happen, then we solve impedance N little t in like exponential in N1 time. So I guess this is the most important slide in the first half of the talk. If you want to remember something, you remember this slide. Yes. Not geometrically, but when we implement the plan, actually Ni is a polynomial in Ni minus 1. Mm. Mm. Yes, I believe so. Mm. So I am going to show it now. If you just want like polynomial time algorithm, then you can choose like Ni to be like a large polynomial or Ni minus 1. And if you only want like infinitely many inputs to be correct, then you can choose the parameter t to be large enough. In our cases, t equal to log n1 always suffices, and then the impedance nt will be like exponential in n1, which means the last case is also polynomial time, and finally every case is polynomial time, and we obtain the improvement. I guess I'll like get into somewhat details into the pseudo-deterministic construction. So I will also introduce the other ingredient, which is a recent hardness versus randomness trade-off presented by Chen and Lizier Chen and Roy Tao. So actually, I want to remark that Roy Tao gave a talk about the new Hardness-randomness trade-off. I think it's also at IAS, and I attended that talk, and that's how I learned Chen Tao. Roy Tao is a brilliant presenter. To give you some intuition on like why we need to use this ingredient, so the following is just intuition, nothing formal yet. So if we know that MIP is equal to NEXP, and if you kind of scale it down, then you get the PCP theorem. Turns out that the Chen Tao generator is the scale down of something. This is so Chen Tao generator is the scale down of some hardness randomness trade-off that follows from IP equal to P space. turns out that if you scale down IP equal to P space, then you get something called the GKR protocol, which is a very beautiful protocol, but unfortunately, we don't have time to go into it today. Then if the insight of Li Jiechen and Roy Tell was to like plug in the GKR protocol. Oh, yeah. Yes. So their insight is to plug in the Chantal generator into what previous people did on randomness versus time. The W here is our algorithm. So it's impactism and Wilson on randomness versus time. And so in some sense, when you scale down the Hardness-randomness trade-off from IP equal to P space, then you get the Chantal generator. And actually, the previous result by Igor and Rahul was obtained by combining a win-win analysis and the randomness versus time framework. And what we do is we combine the iterative win-win analysis with the scaled-down version of randomness versus time and improve the pseudo-deterministic construction to polynomial time. So let me tell you like the result of Chantal generator. The result of Chantal is as follows. Roughly speaking, let f be a hard function. Then we can use f to de-randomize algorithms. But we have some specifications on f. So f is a, here for simplicity, we just take the input of f to be unary, but Chantal considers general binary inputs. So this is not important. So let f be a multi-output function computable by a small circuit. So think of this blue box as the circuit computing f, which has low depth. And let's say the top row is the output of f, where only the first n bits make sense. So the circuit is highly parallel, like low depth. So the width is capital T, which is much greater than D. And let's assume f is hard for randomized algorithms. So of course you can compute f in like T times D time. Oh, I also want to add that we need some uniformity condition on f. So uniformity means given the location of a gate, I can compute the relative information of this gate. Like in Chantal, it was in log space, but so I just want to mention that some uniformity condition needed, but that's just some detail that I want to mention again in this talk. So, yeah. Yes. Yeah. Yeah. Actually, there are some polylog dependence on T. T and N. In our application, you can think of D and N as polynomial and T as exponential. So you can trivially compute the circuit by in time T times D, but we are assuming that the circuit is hard for some time bounds between D and T. So if the function is hard, like for time poly NDS, then we can de-randomize algorithms in time S. Actually, it's I think it's better to look at the generators in a reconstructive way. So let me rephrase the result in the reconstructive way. This is like how the Chantal result was proved. Let f be a multi-output function that is computable in low depth. And now we are not saying f is hard in any sense, but we can always like build a heating set generator from f in poly t time. So to build this generator, you need to examine the whole computational history of F. After you build the generator, you can use it to dynamize algorithms. So there's a reconstruction algorithm that, given any oracle that breaks the heating set generator, can help you compute the output of F. And the reconstruction algorithm running time only depends on the depth, and there are some polylog t dependence which I omit. Hmm? Hmm.
The error algorithm. So you just, if there is a zero error, let's say on the no case, all you want to do is something that will hit every potential zero answer. So you just do. You just need to find one string that fools the algorithm. Zero probabilistic algorithm. So it's two full algorithms that say that if there is a yes answer, half the strings are good. If there is a no answer, no string is good. Then you only need it. It's a weak
Maybe I should also emphasize that by Oracle D avoiding GF, we mean that D accepts like 1/2 of the random strings, but rejects anything from GF. So G is something defined in Chantel. It's not very easy to define.
For many calls.
Oh, it's actually non-black box in the construction of F. You need to do arithmetization on the circuit computing F.
GKR. So it means on GKR and IW. And so it's complicated.
So the upshot is that if I have an oracle that breaks the heating set generator, then the cost of computing F only depends on the depth of F, not on the width of F.
This is a template of all pseudo-random generator, almost all pseudo-random generator proofs there are. You say if the generator doesn't work, this means that some algorithm, some probabilistic algorithm is not fooled by it. And from it, you build a circuit or a Turing machine for the supposedly hard function, and that's your contradiction. So this is that's really a template for all pseudo-randomness, pseudo-random generator.
So the next thing to do is to try to use Chantel to like plug it in and get pseudo-deterministic constructions. So let's first see how to reinterpret the algorithm of Igor and Rahul using Chantel. So the algorithm performs a win-win analysis over two input lengths. N0 is the smaller one and N1 is the larger one. So think of primes as a sequence of oracles. Like for each input length, you have the primes oracle, which accepts a dense subset of strings, but maybe it doesn't accept anything in your heating set generator, because otherwise the construction problem becomes easy. So here we have two oracles, prime on length N0 and prime on length N1. Let's consider the proof.
The distinguisher.
Yeah.
Because of the generator.
It's both an ingredient of the generator and a distinguisher of the generator. It's both an ingredient for constructing the generator and a distinguisher for the generator. So I'll make it clearer later. Let's consider the brute force algorithm that tries to that outputs the first prime on input length N0. So what it does is it enumerates every string. It applies the AKS test on every string, and then it will gather all the information and output the smallest N-bit prime, N0 bit prime. naively, we only have that it runs in 2 to n0 time. But the brute force algorithm has a good point. So its depth is only poly n0. You just enumerate strings in parallel, run AKS on each string, and gather the information.
Low depth.
Yeah.
Yeah, which is all Canton needs.
So now we have a uniform low depth circuit. The natural thing to try is to plug it in Canton. Using Canton, we have a generator based on this low depth circuit. And what we do is we use primes on a larger impedance N1 as a potential distinguisher for the generator. The reconstruction guarantee of Canton is the following. If primes on impedance N1 avoids the generator based on brute force 0, then we can compute the output of brute force 0 in like poly N0, N1 time. So hopefully this is clear.
In this time, you're computing one output, or you're computing all the outputs?
Brute force 0 only outputs one n-bit string, which is the smallest prime on length n0. Oh, I forgot to stress that the reconstruction algorithm is randomized. However, it outputs the fixed output of brute force 0. So it is a pseudo-deterministic algorithm. Now we can perform a win-win analysis. The condition P space equal to BPP is replaced by whether the length n1 oracle avoids the generator on length n0. If it avoids, then by the reconstruction guarantee, we can construct the smallest length n0 prime in pseudo-deterministic poly n1 time. So in this case, we are good. If it doesn't avoid, then we get a heat inside generator, which is Canton on brute force 0 that has sub-exponential size because it and hits primes on length n1. Sub-exponential is because 2 to n0 is like sub-exponential in n1. So in the second case, we get a deterministic algorithm that runs in like sub-exponential time. But we actually get more than this. We can observe like by if you look into Canton and seeing that the generator itself is also low depth, then we observe that the second case is actually another low depth algorithm. So,
Go back to this for a second. So
this one?
yeah. So if it is using Canton on the no one.
Yeah, in the no one, the Canton generator will hit primes on length n1. So,
Maybe I'm confusing. So
It does
if
not avoid G.
right, if it does not avoid G,
So it is fine.
so the oracle does.
is only isn't it the opposite direction? So saying
Oh, so the oracle doesn't avoid the generator. Means the generator hits the oracle. So, so if you want to find something in the oracle, you can just go through the generator.
brute force thing can be done in uniform time, then you get a generator, and then you can hit the primes.
So the question is whether it hits the prime or not. The yes case is it doesn't hit the prime. Then you can use a prime on length n1 to do reconstruction. The no case that it hits the prime, therefore you hit the prime. So our observation is that the second in the no case, we not only get a sub-exponential time algorithm, we get another like low depth circuit for constructing primes. Now let's invoke a third input length. Let's call it N2. And let's consider the brute force algorithm on input length N1 that tries to construct a prime on length N1. So crucially, this is not the real brute force algorithm of 2 to N1 time. This is the brute force on the smaller heating set generator on 2 to N0 time. The heating set generator is the Canton generator on brute force 0. So anyway, using what we already constructed, we now have a 2 to N0 time and poly N1 depth algorithm for constructing some prime, some canonical prime on length N1. And the reconstruction guarantee is still the same. We use the generator on, we use the Canton generator on brute force 1 to try to hit primes on length N2. If N2 avoids the generator, then we can reconstruct the output of brute force on length N1 in like poly N2 time. So let's do the Wien analysis again. Does N2 avoid the generator based on brute force 1? If it does, then we have reconstruction and we can construct a length N1 prime in pseudo-deterministic poly N2 time. If it doesn't, then it's equivalent to saying the generator hits primes on input length N2. Now we have an even smaller size heating set generator that hits primes N2. The even smaller here, it's in a relative sense, not in the absolute sense, because the heating set generator, it's still, the size is still polynomial in 2 to N0, but it's even smaller compared to 2 to N2.
Yeah, what is BF0 we understood, it's just really brute force. You try all the strings and you apply AKS, that's an exponential time. What BF1 does.
Yeah, so from BF0, we can compute the Canton generator based on BF0, which gives you a set, subexponential size set of length N1 strings. BF1 is just, you first compute this set of length N1 strings, and then apply AKS on each of these strings, and finally find the first prime in these strings. Does this make sense?
You find the first string of length N1. That is, so you get a canonical N1 length.
Yeah.
Okay.
So the canon.
That's not a generator. That's an algorithm. It's not a generator.
Yeah, it's an algorithm. The output of this algorithm is the first prime in the generator G of BF0.
Can I think about this instead of looking at this yes/no dichotomy? Can I think about it differently? Saying if BF0 has a uniform fast algorithm, then I'm done. Otherwise, I can use it to build a generator G to the BF0, and that's my generator for the next round. Either that has a uniform algorithm, and then I'm done, or I get a generator for the second round.
Yeah, it's the same. So we can do it again. So as you already mentioned, like if we do three Wien analysis, then we already bypass the half exponential barrier and get something like third exponential. But there's nothing to prevent us from doing more and get ultimately polynomial time. So we have like a lot of input lengths, N0, N1, and so on. We start with the trivial heating set generator, which is set 2 to the N. And we perform a Wien analysis. Can we use input length N1 to try to solve input length N0? If we can, then we solve input length N0. If we cannot, then we get a heating set generator on input length N1 whose size is still comparable with 2 to N0. Then we do another win-win analysis. Can we use N2 to solve N1? If we can, then we use N2 to solve N1. Otherwise, we get a heating set generator on length N2 whose size is still comparable with 2 to N0 instead of 2 to N2. And we perform another win-win analysis and so on. In each iteration, so I think we still need to show this process will terminate at some point. In each iteration, let Ni be the length of primes that we want to find, and Gi be the current heating set generator that supposedly contain an Ni bit prime. So if all of our previous win-win analysis fails, then Gi should contain an Ni bit prime. And let Ti be the size of Gi. Finally, let Di be the depth of the brute force algorithm. But Di is always like polynomial in Ni, so it turns out that it's not a bottleneck. The brute force algorithm on impulse Ni will enumerate all strings in our current heating set generator Gi and output the first prime. Our win-win analysis is we try to use a prime on impulse Ni plus 1 to construct a prime on length Ni by calling the reconstruction algorithm of Canton. If it's successful, then we are successful at length Ni. If it's not successful, then we get a relatively smaller heating set for impulse Ni plus 1, and we can proceed. To calculate the parameters, you can just first Ti plus 1 is some absolute polynomial in Ti. You can think of it as like Ti to the 100th. So, but the relationship between Ni plus 1 and Ni is something that we are free to manipulate. So we can just set Ni plus 1 to be a bigger polynomial over Ni. This will mean that the sequence of Ni grows faster than the sequence of Ti. So although T0 starts as exponential in N0, maybe at some point, Ti will be like comparable to Ni instead of exponential in Ni. And some calculation shows that this is indeed the case. If you pick all log N0 cases, so all log N0 input lengths, then finally T of little t will be comparable with N of little t, where little t is like the number of input lengths we pick. So,
right?
Yeah.
And what will be the final n? And what will be the final n? The final ni when this is terminated?
Exponential in N0.
Time of the generators. What will be the running time of the subsequent algorithms?
You mean the last case or every case?
But when you keep reusing them, the complexity of the algorithms is increasing, right? So what is it? What's the complexity of the algorithm that produces a string of? So if the final ni is exponential, you are going to produce an. Oh, I see. Sorry. So yeah, I guess the point is that you just are shooting for an infinitely often result, and you don't mind outputting a prime of length, some length ni, which may be exponential in N0, as long as the running time is polynomial in Ni.
In current input.
That's okay. So the running time increases all the time with the length of the output you produce, but it's always polynomial in the output you will produce.
So the generator size starts from exponential in the current impedance to polynomial in the current impedance. The running time is like, if you are not on impedance NT, then the running time is always determined by the next impedance Ni plus 1. So we are safe if we set ni plus 1 as a polynomial in ni. Finally, if you are at the impedance nt, then the generator itself is polynomial time, so we can just use brute force. Does this make sense?
So t is going, the number of steps is going to be logarithmic in n0, which is n.
Sorry, reset.
Yeah, t is going to be log n.
Yeah.
So the final n sub t will be exponential in n.
Yes.
Time of the algorithm for generating primes of this length will be polynomial in that length.
Yes. Also, it's also exponential in n. It's polynomial in the current impedance.
There's something I see. Yeah, the problem is defined given n produce a prime of size n, and for infinitely often n's, you don't know which you will between linear and exponential, you will produce a prime of the time. What is the randomness in the algorithm?
It's used in the reconstruction algorithm of Canton. They need to use randomness.
When t becomes close to n, at that stage you don't have a dichotomy, you don't have a win-win. It's just you just know that you're done, right?
Yeah, because the generator itself has polynomial size. You can just enumerate it.
It just becomes smaller and smaller and smaller, and then you just stop when it's small enough.
Yeah. The aim is to show that this case will actually happen. And by some calculation, we can show this indeed happens.
One algorithm, so how do you, is it complicated?
The next slide. Thanks for the question. So since we only aim for an infinitely often construction, we can assume n is equal to some ni. So we just need to be successful on one of ni. If you want infinitely many successful impedance, you can just vary n0. Like the next n0 is exponential in this n0, so that the two n0s doesn't interfere with each other, and you have like infinitely many n0s. Then you can guarantee infinitely many impedance that are successful. So we just focus on some ni. If I is equal to little t, recall little t is the impedance where we have a polynomial size generator. Then we can just find the first prime in the generator gi, which is gt, by brute force. If I is not equal to little t, then we use ni plus 1 to reconstruct ni, which is I have primes ni plus 1, which I suspect should avoid the generator, and then we use we plug in primes ni plus 1 into the reconstruction algorithm of Canton. This will give you hopefully an ni bit prime. To see the correctness, we can also consider two cases. The easy case is when gt contains a prime, then we can just do brute force and get our algorithm on impedance nt. If gt doesn't contain a prime, but we know g0 does, therefore there's some I such that gi contains a prime, but gi plus 1 doesn't. And we'll show that our algorithm is correct on impedance ni. So first, since gi indeed contains a prime, the output of bfi should be the first prime in gi. And second, since gi plus 1 doesn't contain a prime, it means primes on impedance ni plus 1 is a good distinguisher for gi plus 1. And gi plus 1 is the Canton generator based on brute force I. Therefore, we can indeed use primes ni plus 1 to reconstruct the output of BFI, which will give us a canonical prime. So, any questions with this?
I don't understand anyway. So you're giving n as an input, and then what? How do you know if it's equal to so there's some n0 that would hit that n?
Yeah. So let's like predefine some n0. Like the first n0 is a large constant, and then each n0 is exponential in the previous n0.
N0 that would
Yeah, the corresponding n0, and you can also find whether n is equal to ni for some I.
for any n in the sequence or for some of the n's?
Only some of the n. Yeah, we only guarantee it works for infinitely many implements. Yeah, we don't know.
Okay.
Actually, like there's a technical detail where we require a pseudo-deterministic algorithm to remain pseudo-deterministic behavior for every input length, and we don't know if so remaining pseudo-deterministic behavior means something like you cannot have two primes, both are outputted with significant probability. We don't know if we remain pseudo-deterministic behavior on bad input length. So in our result statement, we use an advice bit to encode whether our algorithm maintains pseudo-deterministic behavior. So we get something like pseudo-deterministic construction with one bit of advice. So there's some technical complications here.
It's not completely uniform. It's not completely uniform.
Yeah, that depends on like how you define pseudo-deterministic algorithms in the infinitely open setting. If you yeah, something like that.
So you're saying it's pseudo-deterministic on some infinite subset of the inputs that you don't know, and on the other ones it's completely unpredictable.
Yes.
So you just use the one bit to say which lines are the correct ones.
Which implements obey the pseudo-deterministic
Yes, if you know if you have one bit of advice, then you're
good. So hopefully the correctness is okay. So it seems that we have a compelling story to tell. We have some so there are so many Weyl analysis in complexity theory, and many of them start at like half exponential bounds. And in some cases, we can use iterative Weyl to give you optimal bounds. This has found application in two cases. The first case is pseudo-deterministic construction, and the second case is to prove circular bounds. But the story is not end yet. Recently, a striking improvement by Zeyong showed that the circular bound actually can be proved without using any win-win at all, because somehow you can just win in one case, and you don't need to consider the other case. And
just a second. First of all, you want to take a break, like 5-minute break? Is this a good time to before the next?
Actually, yes, but the first half of the slides are like I still have 2 slides in the first half.
Yeah, okay, very good. So I want to ask a question. Just to summarize where you use the fact that that this works for any dense set in polynomial time, right? So dense set is just you have a. That's why all you need is a heating set generator. The randomized algorithm is a natural one. Pick a random string and see whether it's accepted. Right. So that's where you use the dense set in polynomial time. And there was another place we used the polynomial time assumption was here to test if you actually have a prime or not, right? In this analysis, do you use in the correctness? Do you again use the polynomial time decidability of the set, or it's all?
Oh, I guess polynomial time is like in the brute force algorithm. The depth of the brute force algorithm is polynomial in the input length, because the running time of say AKS will add like poly and we need dense subset because the distinguisher has to be dense. Otherwise, it doesn't make sense to say a sparse set distinguishes a heating set generator. In other words, the Canton reconstruction needs the distinguisher to be dense. Otherwise, it doesn't work.
The Canton generator works also in the two-sided case, no?
For Chantal, it's not the case. You need to take union of some other generators.
So if you didn't use the Chantel in this form, the reconstruction, if you just had a generator, you would still get the existence of a pseudo-deterministic algorithm, but you just couldn't say what it is.
Oh, sorry, could you say that again?
If Chantel was just a generator without reconstruction, just said the statement that lower bound implies randomization, you would still get existence of a pseudo-deterministic algorithm, but you wouldn't be able to say.
Maybe with some small advice. I'm not super sure. Maybe you need some advice. Because maybe on different impedance, it's different, like different algorithms that generate. So I'm not super sure.
I see, right.
So Zhou showed an improvement to our lower bounds, and he improved it to almost everywhere. So he showed there's a hard function in sigma 2 exp that for every impedance it is hard against the exponential size. For comparison, our lower bound is only that the function is hard for infinitely many impedance. And he also improved our algorithm for range avoidance to a true algorithm, which works almost everywhere. Previously, our algorithm only works on infinitely many impedance. And yeah, as Evan suggested, this seems to be a good time to take a break. The second half will talk about the range avoidance problem and how you combine it with iterative win-win to prove exponential size lower bounds, and how you get rid of win-win and prove a true almost everywhere exponential size lower bound. It turns out that the journey starts from some problem in logic, which is about probability of the so-called two-week pigeonhole principle. So maybe let's take a break.
Good, thanks.
Thank you.
5 minutes.
So let's start the second half. We know that the second half is about circular bounds, and we know that Shannon proved most functions require exponential size circuits by a counting argument. Does it work?
Nobody there.
Oh, let me just
Maybe there's a battery or the.
Click on the slide.
Yeah.
Okay. I guess I can just use my keyboard. Oh, I see. Sorry.
Did you?
Yeah, it's working. So, thank you. So, what is a counting argument? Let's review the proof. So, if the size parameter s is somewhat smaller than 2 to the n, then there is an n-bit function that requires circuit size larger than s. The proof is simple. We just compare the number of small circuits versus the number of n-bit functions. If the number of small circuits is less than the number of n-bit functions, then since every circuit corresponds to only one function, there has to be some function that doesn't correspond to any small circuit. The picture is like this. You list all the small circuits, you list all the true tables. Each small circuit maps to a true table, maps to only one true table, and so there has to be some true table that's not mapped by any small circuit. So in logic, we call this the two-week pigeonhole principle. The pigeonhole principle is like if you have more pigeons than holes, you throw pigeons into holes, then there has to be a hole containing more than one pigeon. But here we are considering something different. If you have less pigeons than holes, and you throw pigeons into holes, then there has to be an empty hole. So dual means we have less pigeons than holes, and weak means we have much less pigeons than holes. Hopefully this picture is reminiscent of what happened in the last slide. This is the dual pigeonhole principle is captured by the so-called range avoidance problem. So they are essentially the same thing, but one in the logic world and one in the total function world. In the range avoidance problem, the input is a multi-output circuit C mapping n bits to L bits where L is greater than n. So it's like a circuit mapping pigeons into holes. And your goal is just to find an empty hole. That is a string Y that is not mapped by any input X. We will call such string Y a non-output of C. There is a trivial randomness algorithm for this problem. You just output a random string. It's with high probability not in the range of the circuit. But of course, we want deterministic algorithms. And so we are unable to get deterministic algorithms. And if we get, then it will have dramatic consequences in complexity theory.
So the difference between this and primarities, this is a dense set, of course, the set of Y's. It's a dense set, but we don't have a polynomial time algorithm.
Yeah.
So that's why it doesn't fall in the previous.
Yes. By the way, the primes paper, the primes is also different. I don't know if primes can be reduced to this problem. It appears that if you want to prove density about primes, then appears you need to use more than two-week pigeonhole principle. So I'm not sure if there are like reductions between either problems.
No, but in general, the previous talk, the first hour said that every dense set with a polynomial time verification, and this type of problem do not have polynomial time verification.
Yeah. So intuitively, the complexity seems higher.
So these have non-deterministic polynomial time.
Yes.
So all the stuff that you did before, could you do it for
No, it took what I did before was highly like non-black box. You need to do arithmetization over the polytime property that decides the polytime algorithm. Yeah, so sometimes you can also think of this as a dense co-NP set, because you can verify something is not what you want very easily. So a few years ago, the two important papers, one by Klemberg et al. And one by Oliver Cotton, demonstrated the following principle. If I have a proof by the so-called probabilistic method or counting argument that some object exists or a random object is will satisfy some probability, then finding this object will reduce to range avoidance, and the reduction is essentially the proof. For example, Shannon showed that most true tables require like exponential size. The proof is by the counting argument, and the proof will give you a reduction from this problem to range avoidance. So this problem is a problem of finding a hard truth table. You are given a unary input, like a like a length n string consisting of length capital N string consisting of ones. This capital N will specify the size of the object you want to find, and your goal is to find a truth table of length capital N that requires circuit complexity more than like 2 to n over 3n.
So the circuit in the range avoidance is simply one which takes a circuit and outputs it to us.
Yes, yes. So you can reduce this problem to the range avoidance problem by considering this generator, which we call the truth table generator. The input is a small circuit C, and the output is the true symbol of C. You just want to find something not in the range of this, and you get a hard true symbol. So using this principle, the papers by Klemberg et al. And Oliver Cotton translated the probabilistic proof for a lot of important objects into reduction to range avoidance. So this is a list of objects, and maybe you will recognize many of them. The next topic I want to discuss is, suppose we want to prove circular bounds, but only for some strange looking class like sigma 2e. So what kind of even more strange looking explicit construction notion will it correspond to? A naive answer is so-called F sigma 2p construction, where F sigma 2p means the F in F sigma 2p means functional. So the function you compute will have like multiple output bits, not just a single output bit. And sigma 2p, of course, all we know is the second level of polynomial hierarchy. So it's a non-deterministic machine with an NP oracle. And F sigma 2p construction of hard true symbols is the following machine. First, it's a non-deterministic machine, so it has many computational paths. And second, each path will either fail or output a hard true symbol. And third, at least one path doesn't fail. And of course, it will use an NP oracle. However, if you think about this for a while, this is too weak because an F sigma 2p construction for hard true symbols trivially exists. You can just guess a hard true symbol, use the NP oracle to verify it's indeed a hard true symbol, and if F is hard, then output it. So, what's wrong with this? The answer is that this naive construction doesn't define a hard function. On each non-deterministic path, it will output different hard function. So we will require some pseudo-deterministic like property for this F sigma 2p construction. Turns out that some previous literature called this single valued construction. So let's require each computational path to output the same hard function. It either fails or outputs this particular hard function.
It's somewhat stronger demand than in pseudo-deterministic. In pseudo-deterministic, you could output a few different, let's say, primes. So you just want 90% of the time to get the same prime, and in the remaining 10%, you can get other primes or no answer. Here you want all of the outputs that lead to a function to make it the same hard function.
Yeah, so it's like BPP versus NP.
Yeah.
However, there are also like zero error pseudo-deterministic construction. Then you require every path that fails need to output failure, no different primes. If you look at it a bit, then you will recognize that circular bounds for sigma 2 exp is equivalent to single valued construction of F sigma 2p construction of true symbols. This is not hard to see. Like if I have a hard function in sigma 2e, then I can just print the true symbol of this function. It will give you single valued F sigma 2p construction of hard true symbol. On the other hand, if I have a single valued F sigma 2p construction, then the true symbol that it prints, like it defines a true symbol. So the true symbol it prints corresponds to a function in sigma 2e that's hard for circuits. I think I also want to clarify the parameters here. So the true symbol length we will denote capital N by true symbol length, and the true symbol is a function over little n input bits. So capital N is 2 to the little n, and like by single valued F sigma 2p construction, we really mean polynomial time in the length of true symbol. So it's poly capital N, and it corresponds to a hard function in sigma 2 time 2 to little n. And the circuit complexity is measured with respect to little n. So it's something like super poly in little n, which is super poly log in capital N. So our results stated in like the most generality is a single value at sigma 2p algorithm for range avoidance. So let's give as input a stretching circuit C, and we'll have a functional sigma 2p algorithm that has many non-deterministic paths. Each path uses an NP oracle. This is just saying it's sigma 2p. Then each path either fails to or outputs the same string y, and y should be a non-output of C. And at least one path doesn't fail. And finally, we take poly capital N time. This single value f sigma 2p algorithm will imply sigma 2 exp require near maximum circuit size, as well as single value f sigma 2p construction for all the objects mentioned in the list before, like Ramsey graphs, rigid matrices, and so on. Next, I want to start our journey to go from logic from dual equation principle and step by step and go to our results. The beginning was to investigate this problem. How hard is it to prove the dual equation principle in something called bounded arithmetic? I'll abbreviate dual equation principle by DWPHP. Hopefully it's recognizable. A seminal paper on this topic was by Emil Eljabek, where he proved something like this. Over some theory called S12, the dual equation principle is equivalent to the existence of an exponentially hard traceable. How many of you know the theory S12? Seems that most of you don't know. So it's some weak theory in logic, which you can think of it as the little cat in your house, who is clever, who is lovely, but who doesn't understand the pigeon principle. So the little cat thinks maybe I live in a world where the dual equation principle is false, and there's some strange-looking guy holding a strange-looking circuit that claims that dual equation principle is indeed false for this strange-looking circuit. So he wants to use the strange-looking circuit to achieve compression. For any string y of length n plus 1, you can use the circuit to compress it into a string of length n, and the compression is lossless. Given the length n string x, you can apply the circuit to recover the string y. Since dual equation principle is false, the compression, this compression is possible. So
maybe are you going to say something else about S1, or that's just
no.
I'll say just one thing. I mean, briefly, it's a theory. I believe Steve Cook was the first, or Jan Krajcek was the first to study. It's a fragment of piano arithmetic, which somehow limits logical powers to only polynomial time arguments. It's like proofs that we might, actually.
Oh, I think what Cook studied was PV, and S12 was defined by Bass.
By Bass. Yeah, maybe some Bass defined it. After, So Cook and Krajcek defined, similar classes, and Rasborg also. Anyway, one of the motivations, or at least one of the consequences, was that people made on the question of P versus NP, there seem to be two possibilities. Either they are equal or they are not. But logicians consider a third possibility, that this question is independent, maybe independent of set theory, of piano arithmetic. So a weaker question, or something potentially provable, is that it's independent of weaker theories. And in fact, Rasborg has proved independence not from S21, but from some other limited fragment of piano arithmetic. we show that some circuit lower bound, like exponential circuit lower bound, exactly in this form. Truth tables like this. Proof circuit lower bounds like that for them is independent of some weak fragment of piano arithmetic. I don't know if this means or doesn't mean that we hope that it's really an independent question, but some people feel that it may be in the previous MP may be independent of real logic. So that's a short motivation for this type of theory.
Thanks for the explanation. So I was just trying to present Emil proof as like some compression game.
Yeah, no, that's very good.
Thanks. So to decompress a length n string, you just plug it in the circuit C, and to compress the string of length n+1, you find, let's say the lexicographic first x such that Cx equal to 1. Let me remark that compression is an empirical. This will not be important here, but it will be important like when we translate things into the total function world. So you can compress n+1 bits into n bits, but apparently that's not enough. And let's say, what if we want to compress 2n bits into n bits? It's easy. You can just compress the strings 1 bit by 1 bit. So suppose you have a 2n bit string, you compress the first n+1 bits while you just keep the last n-1 bits unchanged. Then you get a 2n-1 bit string. You compress the first n+1 bits again while keeping the other bits unchanged. You get a 2n-2 bit string, and so on until you find until you get an n+1 bit string, and then you compress it. So the compression goes down while the decompression goes up. So if you have a length n string, you just plug it here and decompress like n times, you obtain the length 2n string. So in like more formal words, this shows dual equation principle from 2 to the n to 2 to the n+1 is equivalent to dual equation principle from 2 to the n to 2 to the 2n. And even that is not enough. We can do something like more fancy. We want to compress a super long string T into capital N bits, while we also want local access to the long string. What is local access? So it means given an index I want to compute the ith bit of T very fast. We don't need to reconstruct all string T. We can get the ith bit in polylog T time. Then the compression guy will need some other help, which is to use GGM tree. GGM stands for, you probably cannot see it here. GGM stands for Godwin-Mikali, which is, and the GGM tree is the technique they use to prove pseudorandom generators are equivalent to pseudorandom function generators. This tree also has a lot of other applications in TCS, such as Merkle tree, and of course, this Yajabek's proof and Paris-Wiki-Wood's proof of pigeonhole principle, and so on. Anyway, it has a lot of applications in TCS. So let's say we have a super long string. We cut it into length capital N small parts.
This n is in the. This is 2 to the 4n or 2 to
yeah, 2 to the 4. Yeah, because what I draw here is exactly 16.
Yeah.
Okay, then you compress every segment of length 2n into length n. Then so the length of the string like shrinks by half. Then you shrink it by half again and again, and until you obtain a compression of length n. So you get something like a binary tree. So given a long string of length t, you compress it into length n, and this is let's say if you want local access to the nth bit of the long string, then you can just start from the root and walk along the tree, something like this. So we first decompose the string, and if we know I, then we know which direction to go, and we do it again and again until we can reach the nth bit of the original string. So this time it's polynomial in the decomposal circuit, but it's polylog in the length of t, polylog in t. So in our setting, it will be quite efficient. Now you see, like, if the dual equilibrium principle is false, this will give us a fancy word for compression. Not only can you compress any string into length capital N, you can actually do the decompression locally, and these strings, if you will them as true symbols, will have small circuits. So you have this string, you compress it into length N. The length string will give you a small circuit for computing the true symbol. You just hardcode the compression, and given I, you work on the GGM tree. Stated in more formal terms, it's like if my weak theory cannot prove the dual equilibrium principle, then it will also think every true symbol has a small circuit. I hope this is understandable. But if you look at this theorem contrapositively, then it's like, if I have a hard true symbol, then I can use it to prove the dual equilibrium principle. Oh, I forgot about some remark about parameters. You can just set, if you care about suited epsilon size for fixed epsilon, then you just set the true symbol length to be a large enough polynomial in over the size of the circuit, then we are fine. So now, if we think about this statement contrapositively, it's saying, if I have a true symbol that requires large circuit complexity, then I can use it to prove the dual equilibrium principle. So prove this man wrong. This is the observation by Oliver Canton. He found that Iterative proof actually implies constructing true symbols with high circuit complexity is, in some sense, the hardest explicit construction, because it's as hard as the most general range avoidance problem in some sense. So let me reveal the previous insight as a reduction. The reduction appears in Canton's paper, so I'm calling it Canton's reduction. What the reduction does is, given a circuit C which we want to solve range avoidance, and also given a hard true symbol of length capital T, so think of capital T as some parameter. Maybe it's poly n, or maybe it's larger. So we have a hard true symbol. I didn't draw the circuit here. The output should be some string y that's not in the range of C. So you still want to solve range avoidance, but now you have the assistance of a hard true symbol. And Canton showed that we can do it in polynomial time with an NP oracle. This is how the compression needing NP oracle comes into. So we first construct the GGM tree, and we distribute the hard true symbol into the leaves. We first, for each non-leaf node, we use the NP oracle to find the lexicographically first preimage of its two children. This step needs an NP oracle. Also, to make Canton's reduction well defined, we require this to be lexicographic first preimage. So anyway, if the length 2n string is indeed compressible, then our NP oracle should successfully find the lexicographic first preimage, and we should be able to extend the GGM tree, and so on. until at some point we fail to invert we fail to compress the length to n string, which means we find a non-output of the circuit and we solve the range avoidance problem. And after this happens, let's just make everything afterwards to be like the special failure symbol. Now we have this reduction that given a the process has to fail somewhere because we are provided with a hard truth table. If the process didn't fail, then the truth table is easy. And the place that we fail will give you a solution to the range avoidance problem. No.
How do you use the truth table? You just break it into chunks
Yes.
of length and
Yes.
try to compress each pair. So it's just it's not it's a string.
Yeah, it's just a string.
Yeah. So you,
But it's a truth table with large circular complexity. So if you manage to compress it all the way down to root, then the truth table will have small circular complexity. So we use it as a truth table in the sense that we consider circular complexity.
It's enough to look at like linear depth, I guess, circuits.
Linear depth? No, because each step we will use the circuit C. C is our input for range avoidance. If C is an arbitrary circuit, then we cannot say anything about restricted circuit. And in our lower bound proof, we will not only use Canton's reduction, but also use the so-called computational history of Canton's reduction. So Canton's reduction is a well-defined P2NP function. So given a stretching circuit and a hard truth table, it will output a non-output of the circuit. And we define history of Canton CF as follows. So basically, it's the whole GGM tree, also with the place where Canton's reduction fails. So first, we write down the original truth table into the history, and then each time we compress successfully, we add the newly added node into the history like this. And when we fail, we add the failure symbol into the history, and then everything afterwards is failure symbol. And finally, we record the index of the node that we fail into the history. And given the history, it's very easy to compute the output of Canton. So you just look at the index, and the index tells you where it fails. Then you can find a non-output of the circuit. And there's something, don't be scared about this. There's something about local verification of the history. This is the property that we'll need. What does this mean? So we will perform some local tests. And the history of Canton will be the only string that can pass this local test. Let me describe what the tests are. First, we have the failure index at the end of the history. So for every I less than the failure index, it should compress successfully. And for every I less than index, the compression is not only successful, but also gives you the lexicographic first pre-image. Lexicographic order is arbitrary, but we will need to fix such an order so that like the execution of Canton is well defined. So we will make compression at each node before index. And then we will check something at the index node. We will check that it's a non-output. So this corresponds to, for every value we prime, say of we prime is not equal to the output of Canton. So we will do something here. And finally, we will check that everything after index is a failure symbol. We claim that history CF is the only string that passes this group of local checks, and also I think this claim is not hard to see. And what is the pi1 local? What does pi1 local verifier mean? So we have exponentially many checks, right? Think of capital T as maybe exponential in n, and we also have like polynomial in 2 to n checks because we need to check it for every index and for every possible preimage. So this is like a co-NP machine performing the check where it universally guesses some poly n bits and then looks at the history for poly in many places and then tells if the check is successful or not. The upshot is that we have some co-NP machine that has, let's say, random access or oracle access to the history and uses some universal quantifier and reads the history for poly many times and then accepts the history if the history is exactly as defined and rejects the history otherwise.
What is the input to this quantum machine?
It has no inputs, but it has oracle access to the history.
To something which may be a history.
Yeah, so you can think of the input as history.
Yeah. So the length of this history is T, O of T.
Yeah. Now the history is very long, but we will use a win-win argument depending on whether the history is compressible. So let's FB. So let's say we start with a some kind of brute force string, like any string not in the range of GGM tree. For example, we can just concatenate every length 2n string together and get a like length exponential in n strings that is not in the range of GGM tree. Then we apply Canton to this super long string. This is equivalent to using brute force algorithm, enumerating every non-output until you find one.
What do you mean by the range of the GGM tree?
Oh, so it's like I have a circuit from n bits to 2n bits, and I build a GGM tree like this. So we get a new circuit from n bits to t bits. So if f is a string not in the range of this circuit from n bits to t bits, then Canton's reduction will be successful.
That's for a specific C, for a specific stretching function.
Yeah, or you can also think of f as a hard truth symbol. But here I'm just using that. Here I also need to use that. You can you can express the brute force algorithm also in terms of potence reduction. You just build a large enough exponential size GGM tree, and you plug in some brute force f. So we have this brute force f, and we run Canton on it, which is equivalent to the brute force algorithm where you enumerate all strings and find the first non-output. And we consider the history of this. We consider the history of Canton running on this brute force string, and we do a win-win analysis on whether history has small circuits. So we consider whether this string, which consists of our brute force string, and then a list of preimages, and then a list of failure symbols. We consider whether this has small circuits. If the history has small circuits, then we claim that Canton's reduction can be simulated by a F sigma 2p algorithm. Of course, Canton's reduction is well defined, so it will output some particular string, which means the F sigma 2p algorithm is single valued. Each branch will output the same string. And how do we simulate it? We use the first existential quantifier to guess a small circuit D that represents the history. And then we use the universal quantifier along with the checks I mentioned before to verify the circuit indeed encodes the history. So if there's a small circuit for the history, then I can guess the circuit and I use the checks like before the index, after the index, and after the index to verify the circuit is a valid history. This means that if history has small circuits, then you can find a non-output of C by a F sigma 2 single value F sigma 2P algorithm. Does this look like reminiscent to something to you? This is the Capleton theorem, in some sense. So it's like if my exponentially long string has a polysize circuit, then I can verify it. Well, actually, it's like if some computational history, which is a very long string, has polysize circuits, then I can verify it in sigma 2. It's morally similar to the Capleton theorem. But what if the history string is hard? Although in this case, we don't immediately get exponential response.
It's not just morally similar, it's the same proof.
Oh yeah, the proof is the same.
So you guess the circuit and
Yes. So we get something. If history is hard, then we know we can produce the history in 2 to the n time with n pure arco. But now, let's say, history has like circuit complexity at least n to 100. This is not something we know how to construct unconditionally. So we get something here. So let's try to use this history, which has large circuit complexity, to solve range avoidance on a larger impedance. We fixed a larger impedance N1, and we use the history at so let N0 be this capital N, which is the initial impedance we are considering, and we consider larger impedance N1. So we use history on this N0 to try to solve range avoidance on N1. You can just plug it in Canton's reduction. Then we have another history, which is the history on impedance N1. Previously, we are using history on impedance N0, and we do a win-win analysis over whether it's a hard cycle. If it is hard, then we use it to solve N1. Now we have a history on N1. We discuss if this history is easy or hard in terms of circuit complexity. If it is easy, then we can solve range avoidance on impedance N1 using a single value F sigma 2P algorithm. And if it is hard, then we can look at another impedance N2. And since history on length N1 is hard, Canton of this string on N2 can solve range avoidance, and then we look at the history on length N2 and do win-win analysis and so on. If you don't understand this slide, it's okay, because this slide doesn't present the state of the art anyway.
But still, I mean, this is much simpler than the primarity.
Oh, yeah, I see.
You don't need this generator of Canton, you just have the,
I see.
you have these quantifiers that, you know.
Yeah.
I mean, conceptually, it's simpler than the primarity one.
That's true.
Can you think of primality as range avoidance somewhere? Can you think of primality as range avoidance?
I'm not sure, because
Multiplying.
I mean, I don't know of a proof of prime number theorem using dual-equation principle. It seems that something like stronger than dual-equation principle is needed.
I think what that means is that primes are exactly the outputs that are avoided in a circuit that takes two numbers and multiplies.
Yeah, this
Doesn't have to be exactly right.
Not exactly, and there are many.
the circuit, technically the circuit is not stretching, I think. If you want to make it stretching, maybe you need to use more work. So I guess you need some work to make it stretch. Oh, actually, Oliver Canton has a paper which according to him, he translated some proof by Paris Wiki Woods, and he reduced the finding parameters to some sort of range avoidance with factorial R. Then let's look at something that doesn't need to use Wien analysis. We can actually like one case of the Wien analysis always holds. So we don't need to consider the Wien analysis anymore. The new insight is to consider Canton's reduction and its history in post order. So it's like DFS order, depth first search order. We still look at Canton's reduction using the naive string, and we build the GGM tree from left to right. And whenever we can advance, then we advance. So for example, we have these two nodes here, and if we can compress the two nodes, then we compress it. Then we do the same thing, and crucially, if we can compress the two nodes we already have, then we compress it. And then we do the same thing. If we can compress two adjacent nodes, then we compress it. Until we arrive at some place that we cannot compress. Then we find a non-output of C, and then we fill the rest of the tree by the failure symbol. So we just consider history of Canton's reduction in this order, and it turns out that this history always have a small circuit. What you do is you just store the deepest nodes, and there are only like all capital and many deepest nodes. So this gives us a true single-valued F sigma 2p algorithm for.
Can you say what the circuit is again?
The circuit is you just need to store these 4 nodes, and if you want some other nodes in the tree, then you compare against the 4 nodes. If it's like a descent of some nodes, then you can apply the GGM construction to retrieve that.
You need to reverse the GGM.
Oh yeah, use the decompression.
But what about things that are after?
After, they are always the failure symbol.
Yeah, failure.
Yeah.
No, I'm saying things that are after just because you started with a trivial string.
Yeah.
So you know what they are.
I guess if you mean the leaves, I guess that's not important.
Yeah, or the leaves or not.
I guess that's not important. But for the non-leaves, you just assume they are failure symbols. So on input circuit C, what we do is we get a compressed version of history, which consists of a few nodes, and they will extend to a whole GGM tree. If you want to know like what's the value at this node, then you first see if it is like a descendant of some string in the node you guess, and if it is, then you run decompression on GGM and get what's this node. Otherwise, it's just a failure symbol.
So again, what is the algorithm here? You're looking for non-output, right?
Huh?
You're looking for a non-output.
Yes.
Yeah. So what is the algorithm for finding a non-output? What is the circuit? Sorry, the circuit is these 4 nodes.
Yeah, I haven't described the algorithm yet.
Okay.
But roughly speaking, you guess the 4 nodes or all n nodes. You expand it into the complete GGM tree.
And this you need the alternate, the NPO.
No, this part just needs one existential quantifier.
Or
The NPR code is used later to check the history is correct.
no, you need the lexicography first. So don't you need an NPO?
Actually,
The DGM, the way you define it, you are looking for the lexicographically first.
but now we are just guessing some history. We will verify everything is lexicographic first later using an NPR.
The lexicographically first is when you're going down, when you're compressing. If you're starting from the bottom going up, there's always a unique way to do it.
Oh, but when you start from the bottom, it's not necessarily lexical first. So you still need to verify it.
What I've said, you use lexicographic first on the way down.
Yeah. So I mean, if you guess the compressed version and decompress it from bottom up, then there's no guarantee that everything is lexical first. So you still need to verify it. To verify it, you just use the verification that I mentioned before. You verify everything before index is correct. The node at the index is a non-output, and everything after the index is failure symbol. So actually, this is a complete description of the single value sigma 2p algorithm for range avoidance. You just guess a compressed version of history, then you use an NPR code to verify it. Then you can read off the non-output from the history. Is this okay? Then it's easy to see this is a sigma 2p algorithm and outputs a non-output of C, and moreover a single value because it always outputs the output of Canton's reduction, and Canton's reduction is a deterministic procedure. So this algorithm implies an exponential set lower bound for sigma 2e. With some more work, we can also obtain a single value S2p algorithm and prove lower bounds for S2e. S2e is the symmetric alternation class. I didn't have time to define it here, but roughly speaking, it's something between P2NP and ZP-P2NP. So you can think of it as randomized version of P2NP. So we can prove circular bounds not only for sigma 2e, but also for this seemingly smaller class S2e. And the more work, it's very interesting to note the more work here refers to like 15 pages in our paper, but only 2 paragraphs in Zeyong's paper. And finally, I want to end the talk by some open problems. Basically, every movie analysis represents an open problem. Can we improve it? Here are some of I think pretty major movie analysis where we are stuck at improving them. It's very interesting that we got improved algorithms for we got improved pseudo-deterministic algorithms and improved lower bounds for sigma 2e, but only this. We are trying to prove exponential set lower bound for MA EXP, but we don't even know where to start. Like anyway, we are stuck at all these problems. And for example, another interesting example is the randomness versus time, where Russell Pagliazzo and our evaluation showed that if EXP is not equal to BPP, then we can get subexponential time generalization of BPP subject to some caveats like average case and infinitely often. But they need to use win-win analysis on whether EXP has small circuits, I remember, So the argument doesn't show if exp is exponentially hard for BP time, then we get polytime randomization of BPP. That's another interesting test case for iterative win-win arguments, which we are currently not making progress. And finally, our pseudo-deterministic algorithm is two-sided error. So there are always some branch which, there are some branch which will output different primes, although the fraction of this branch is exponentially small. Igor and Rahul used another win-win analysis to get rid of this two-sided error and get zero error pseudo-deterministic constructions. But we don't know how to make our polynomial time algorithm also zero error. If we use another win analysis, it appears that we start at half exponential again. So I think these are a few open problems on win analysis that one could try. And depending on whether you believe in win analysis, it's meaningful and interesting. There are two cases. If you believe, then can you obtain optimal win analysis? And can you get iterative win from art to science? So currently, it seems that we just apply it and it works for some problem, it doesn't work for other problems. Do we have a good explanation of what problems are suitable for iterative win-win? And if you don't believe it, can you get rid of win-win, just like what Zeyon did for the new circular bond? Can you make it useless? And I want to thank you for attention.
Thank you. Questions? Do you think it may be easier to de-randomize pseudo-deterministic algorithm than general randomized algorithm?
Well, first, since for decision algorithms, they're the same.
No, for third problem.
You mean to randomize pseudo-deterministic algorithms compared to general algorithms?
It may be easier to take your pseudo-deterministic prime generating algorithm and make it a deterministic one than to de-randomize PPP in general.
Oh, I'm not sure. De-randomizing pseudo-deterministic search algorithms is like de-randomizing decisional version of PPP, right? You mean if you mean in general?
Yeah, I mean in general, or I mean in any your own results, your results about dense polynomial time checkable sets. You have a particular probabilistic algorithm for this, which is pseudo-deterministic. The question is whether this will lead to a deterministic algorithm for the same set or not.
Interesting.
This may be easier than PPP.
I see, for the specific set primes.
Let's say primes or dense, yeah.
Actually, I'm not sure. I still think you need to use some structural properties of primes or something like that to get deterministic algorithms.
Okay. More questions?
So you really needed the Canton generator to get the previous results on prime. Is there like other kinds of generators that if you had those generators, you could do more things or?
Oh, that's a very interesting question because I have a feeling that iterative win-win, I mean the kind of iterative win-win I have seen all rely on hardness versus randomness trade-offs. You can treat Canton's reduction as a hardness-randomness trade-off. If I have a hard stable, then I can solve some generalization question, which is to find non-outputs of straightened circuits. Does this make sense? So, so maybe in some cases, you just need to figure out what's the right hardness-randomness trade-off in order to apply iterative win-win. But I think we still need to think more about this phenomenon.
So what happens if you I guess if the range avoidance question was stated with a constant depth circle, for which we have lower bounds, does this imply, or maybe it was easy before, to just solve range avoidance in constant depth? I guess here you could apply a pseudo-random generator. Okay, I take back my question.
Range avoidance for constant depth circuits is also studied in a few papers. It appears harder than proving lower bounds.
The generator wouldn't give you an output that's not in
The generator, well, okay. Maybe I will not take my question, I will just.
So it depends on a lot.
I think range avoidance, even for local circuits, where every output depends on 3 or 4 inputs, that's already hard.
It also depends on the stretch, like whether you stretch n bits into n plus 1 bits or like n squared bits.
So, okay, good. So we have lower bounds.
You have lower bounds, but you don't have range avoidance.
Like you say, if we have a hard truth table or hard function for some class of circuits, then we can solve range avoidance for circuits from this class, roughly.
Oh, you mean Canton's result?
Yeah,
Yeah, but the overhead is large.
the overhead is large.
Yeah, because you need to compose your range avoidance circuits like a few times, and then you need to prove low bound against this.
Okay. Oh, yeah.
Okay, so I guess is win-win analysis controversial somehow? Like I'm curious about your yes and no here.
Actually, not so controversial among competitors, I guess, but it certainly limits the application. Like you don't hope to really use our algorithm to find primes, because maybe among impedance 100 and 2 to 100, there's only one impedance that succeeds.
Okay.
Win-win goes back, I don't know, 50 years, right?
Yeah.
When you think of Cannon's law about this. Yeah.
So it's not
Because,
something
yeah,
like
That's not, well, it's not controversial. I mean, you can call it case analysis and it doesn't sound.
I was curious if it was something like you were talking about, like some statements could be independent. Maybe.
In this sense, yeah.
I don't know.
No, I guess it's, logically fine. I think the kind of things that may be independent are of the nature of this pigeonhole principle type question. I mean, they seem to be somewhere, maybe somewhat related to questions that are really independent of set theories that have to do with, I don't know, really different infinities or like coins, maybe. I mean, I think that's some of the intuition. It's supposed to be finitary analog of real independence results like coins. All right, thanks again.
Thank you.